Hello, everyone. It's really nice to see so many of you here. So let me start with a question. How much time and effort do you spend writing new code compared to the time you spend reading and understanding existing code? So if you're like me, understanding code takes much more of your time. Whether it is to add a new functionality without breaking the existing one, or fixing a bug in code you're not familiar with, or doing a code review for your peers. And in most cases, the code is not yours. So if the task of understanding code is so important to most of us, I think it's for everyone's benefit, including your employers, that you spend effort writing code that is readable and easily understood by all the members of your team. My goal with this talk is to collect and summarize advice to write code that is easier to understand. And I've tried to fit as much as I could in 1 hour. So I target beginner to intermediate level developers with the objective of talks like this one being part of onboarding process, for example, for new colleagues and coworkers. You'll note that I added numbers to the slides, so I'll take questions at the end. A little about me. My name is Vincent Zalzal. I've been using C++ professionally for 15 years now, and I've been using also C# for 2 years. I've used MATLAB and Python for projects at work and some Rust at home. I've worked mainly in the computer vision industry doing 3D reconstruction and sensor calibration. So I get to stare at those lovely distorted calibration grids like this one and try to make them look straight. Oh yeah, also I've worked in a 30-year-old code base, so I've seen my fair share of hard to read, hard to refactor code. But to be honest, the argument goes both ways. I've written some pretty arcane code myself, and so that's why now I advocate for simplicity. So let's start with some general advice. There are different kinds of talks. Some are factual, for example, presenting some new C++ features. And others, like this one, are based on opinions. So yeah, it's true. These are mostly informed opinions based on experience, mine and mostly the experience of others. But it's still anecdotal evidence. Like it's not as in math, for example, where you can have a logical proof that something is always true. Or not, most of the time, not even at the level of science, for example, where you can use a scientific method to compare two code bases, one that uses a guideline and one that doesn't. So guidelines are usually not absolute. Keep that in mind. Take them with a grain of salt. Those that I will present in this talk and others, and even in books. Use your judgment, be pragmatic. Also, it's very important that you build consensus among your coworkers and you decide among yourselves about those guidelines. You won't change many people's mind by submitting code that goes against the current guidelines. If you think a guideline is wrong, discuss it with your colleagues and be ready to change your own mind because they will try to convince you. So be open-minded. Before going on with the advice, I want you to have in mind there are many different environments in which we read code, each with different levels of comfort. So the most comfortable, unsurprisingly, is your IDE. This is where you have the nice syntax highlighting, nice tooltips that tells you about auto type inference and parameter types for your functions. So this is the easiest. Next level down, you have your local tools like diff tool, version control, and well, you still have syntax highlighting, but no more tooltips. So at this point, if you need some help, you still have the code accessible locally. So worst case, you fire up your IDE and you're good to go. But one level down, this is where conditions might become hostile at some point because now you're using remote tools. And at that point, the code is new to you. So let's say you're looking at a pull request on GitHub. This is code that probably nobody has seen before. Also, usually you will only have a few lines around the diff. Maybe if the function is very long, you don't even have enough context in that small window to understand if the change is correct or not. You won't have IDE tools to help you know, oh, what's the return type of this function? What's the parameter of this function? And if you want to do some code lookup, they're really more expensive at that point, because now you have to git stash your local changes, change branch, then fire up your IDE, do your code lookup, and then you have to revert everything back to get back to what you were doing before. So I want you to keep in mind the GitHub reviewer as an objective, like make their life easier and help them think and reason locally. Here's a very simple procedure that I suggest to improve the readability of your code. And you'll see it's very easy. First step, write your code. So that's the unsurprising part. And when you're about to submit it, first take a step back, look at your diff, check that it makes sense. But even more than that, I want you to imagine that you're doing a live code review with one of your coworkers. And I really mean it. Like, pick one specific coworker and imagine you're trying to explain to them why you did things the way you did it. And if you need, what do you need to say as clarifications for them to understand your change faster? Could you name things differently, for example, because you're using some naming conventions or common idioms in your code base so that they would understand faster? Every time you felt that the need to add a clarification, maybe because a name was unclear or a function was too long, then maybe it's time to modify the code before submitting your pull request. And in the worst case, if you have to keep the code the way it is for example, performance reason, then maybe it's a justification you need. And now you can add comments to justify why you did it the way you did it. Now for something that's dear to my heart, the C++ core guidelines. So for those that don't know, it's a big markdown file with a lot of guidelines that summarizes the best practices to write high-quality modern C++. It's been spearheaded by Bjarne Strastrup and Herb Sutter, but last time I've checked, there were more than 300 contributors on that single file. So by looking at this, you're looking at the distilled experience of a lot of people in the industry. So following those guidelines should improve the way you code. It's a big file. It's 2,300 lines long the last time, 23,000, sorry, lines long the last time I've checked. And for the anecdote, I've tried doing some git blame on the GitHub webpage, and the webpage timed out. So that's how long it is. I suggest even, it's not been meant to be read from top to bottom, really. It's more like a reference, but still I suggest that you read a few every day. Carve a portion of your day, for example, during your commute or at the start of your day, and read a few every day. And it will improve the way you code. This talk relies a lot on the core guidelines. So every time you'll see a box like this one with a number in it, it's actually referring to one of the guidelines. So you can just open that markdown file and search for the number in the box. Software developers like to solve puzzles. Yeah, first you have to solve the actual problem you want to solve, find the right algorithm to solve it. But even in the code, when you're writing the code, you're thinking, oh, I have this loop and I have some code outside of the loop that's repeating the code inside of the loop. Can I rewrite this differently so there's no repetition? Or maybe can I avoid the loop completely and use an algorithm? But I will need some lambda with clever captures, and at some point you get the idea. It's the joyful moment, you have the solution to your puzzle, you have that rush of dopamine, you're happy, you're feeling proud, you want to share with the world your ingenious solution. But I want to be the one to say add a fourth step at this point. And think, it took you some time to reach that point. Are you leaving behind a puzzle for your readers to understand? If it's the case, then maybe you should choose the less clever but more obvious solution, even if it's not as satisfying. So don't prove your value with clever code. You should use simple constructs when possible and idioms that all your colleagues will understand. Another advice is to reduce the cognitive load. So here's the definition I'll be using in this talk. It's the number of things that you have to keep in your head just to be able to wrap your head around the block of code that's in front of you. It's the extra context that you need that is out of your current view to be able to understand it. Cognitive load is what is draining the mental energy of your colleagues. And so you want to reduce it as much as possible. Here I've listed some of the C++ core guidelines that help reduce the cognitive load of your code. So the first one will be pretty obvious to most of you, write short functions. It doesn't have to be a very specific number of lines. I know Ben Dean this morning said his average is 5 to 6 lines, but honestly, I don't think it's the number that's important. It's just keep in mind that longer functions are harder to understand. They need more context. And if you feel the need to add comments that says, step 1, do this, step 2, do this, then maybe it's the right time to consider splitting into subfunctions. And even maybe there's no comments, but there's blank lines separating the blocks of codes that tells you, oh, maybe it should be split at this point. Second point I want to talk about is leveraging what the compiler can write for you. So the compiler can write a lot of code that will be correct and fast, and this will reduce the size of your code base. We'll talk about this later on. Express intent in code as much as you can instead of comments. So the first one will be also quite obvious. Use good names. This is difficult, but worthwhile, especially for functions, I would say. Choose good names for your functions. And this is where I will also add, using naming conventions can be really good. It adds more meaning that is common to your team, and you can help new colleagues by having a list of your naming conventions, and they will boot up faster. Also, if you have any kind of assumptions in your code, and it's only in comment, it's always better to add an assert next to that comment or replace the comment altogether so that you're sure that this assumption will stay true in time, even after refactorings. Next advice, avoid global state. Again, something that we hear often. Having mutable global variables is like an invisible link between different parts of the code base. And it's very hard to know which parts of it need to read it and which parts of it need to write to it. And it's pretty much agreed upon now that using mutable singletons is the same as using global variables. So when you can, avoid it. If you need to pass more parameters, do that. I'm very excited actually to try out what also Ben showed earlier this morning to use global APIs in his keynote, so I'll be looking into that. I would push this one step further and say that if you have classes with a lot of data members in it, it's pretty much the same as global state at some point, but at a smaller scope. If you look at a member variable, if your class has a lot of data, then it's the same as if it was taking all the data members as non-const reference. So how do you know which data member is modified and which is read by that function? So try to reduce the size of your classes in general. Finally, promote local reasoning. So this comes mainly through, for example, pure functions. Writing pure functions is really having a function that depends only on its inputs. It has no dependency on some external state, and it only produces outputs, no side effects, no mutation involved. So think square root. It's a very easy function as an example. And having that makes it way easier to understand and test. Also use const whenever you can, even for local variable. For example, when you read that the declaration of a variable is const, you don't have to hunt everywhere in the function to know if the variable has changed. Don't worry, there's code in this talk, and it starts here with classes. So let's start by reducing the total amount of code by letting the compiler write code for us. We'll look at three things: special member functions. So these are your constructors, destructors, copy and move operations. We'll look at comparison operators, and we'll look at aggregate initialization. The benefits of letting the compiler write those for you is that first, your code base will be smaller, so easier to wrap your head around. And especially the behavior of those functions will be unsurprising because everybody will know that, oh, it's the default compiler generated function. I know what this does. Also, you will require fewer tests and your tests will run faster. The code the compiler generates will be correct and fast, usually as fast or faster than the one you would have written yourself. So let's look at special member functions first. Here we have a simple class with a float and a vector. And let's assume that you write nothing else. Here, on demand, the compiler would generate all of those functions for you. It would generate the default constructor, the copy and move constructors, the destructor, and the copy and move assignment operators. And they all do kind of the same thing, member-wise operation. So they will just copy each member or move each member and so on. Here, they do the right thing, and it works well because each of the data member is handling its own resources. It works here because vector is doing its copy itself and correctly, and it knows how to destroy itself. So you should always strive to do that. Let the data member handle their own resource, and don't let the compiler write those functions for you. And this is what we call the rule of zero. So don't write, as I said, don't write special member functions. Each data member should manage its own resource. As an example, let's say you have a class with a non-trivial destructor. And let's say you only need that destructor because of one of your data member. Maybe it's a good sign at that point that you should push the code of that destructor down inside of your data member and replace it with some new abstraction that would handle all that for you. And then the default destructor would do the right thing and you wouldn't need it anymore. What's even better, it's at that point, that new abstraction that you created, probably you will reuse it elsewhere. It's the same thing for copy semantics. So probably what the abstraction you've done, you also required to specify the copy semantics for the same reasons. I would also add another point. Let's say that the default copy semantics are not valid for you for some reason. If you don't need them right now, I would say, worst case, delete them until you need them. Because anyway, usually we don't like to copy things. So maybe you can wait. Wait until you require it. Let's look at this copy constructor as an example. So this copy constructor for widget has two parts. The first part here is the member initializer list, and it's doing some pretty trivial work. It's copy constructing each data member. This should raise a red flag when you see this. You're kind of listing all of the data members and doing trivial work. This is clearly something that the compiler can do for you. And why couldn't we let the compiler do this? In this case, it's because of the code in the second block. And here, there's some handle that needs special care for copying and allocation. So because of that fourth data member, we couldn't use the default copy constructor. And this is the perfect example where probably you should push that code down into a new abstraction, replace the handle by that new abstraction. And now you don't need to implement the copy constructor anymore. The default one will be correct. Now let's look at comparison operators. Again, very simple class, a name with two parts, family name and given name. And let's assume for now that in your code base, it's a very common type. You need to provide convenience functions to do all kinds of comparisons with that type. So you would need normally to implement all those 6 functions here. And this is very tedious, very error prone. Normally you will do a lot of copy pasting when implementing those because they're very similar. So there's a lot of chance that you will make a mistake doing that copy paste. And did you really test those 6 functions? So since C++20, we can let the compiler write this for us now, which is really nice by using the 3-way comparison operator. So this is what it looks like. It's also called the spaceship operator often because of the shape it does. And you could implement it yourself, and then it would replace all those 6 functions previously. But even better, you can default it, which is new. And this is really nice because it will have the same kind of behavior as the special member functions. It will do member-wise the operation. So in this case, for example, it would sort by family name first, and then if the family names are equal, it would sort by given name. One thing to keep in mind, now the declaration order becomes important. So be wary of that. To push the simplification even further, if your class has no invariant, use a struct instead. So this assumes a convention, a very common convention that says if your class has only private data members, you should use the keyword class. And if your class only has public data members, you should use the keyword struct. You don't have to do this, but again, it's adding more meaning to the keyword. So it's a good idea to use that convention. And assuming it, then what this really says is if a class has no invariant, all its data members should be public. What do we mean by invariant? It's a constraint on the data members. So imagine you could take any combination of all the possible values of your data members. Are they all valid? If not, then there's a constraint between them, and there's an invariant. And it's the responsibility of your class to enforce it. If there's no such constraint, and each data member can vary independently, then just use a struct. And it will also enable later aggregate initialization. Here we have an example of, again, a small class with a score entry, with a name and a score, and 2 constructors. So let's look at the second constructor. This constructor is like a convenience constructor, just passing on every input to construct each data member. Here we see that it's doing some trivial work. It's repeating every argument. So again, red flag, oh, I'm repeating all the data members. And often the classes will be bigger than that. They might have 4 or 5 data members, and it's very common to provide those constructors for convenience. But you can let the compiler write this for you again. It's the compiler's job. So also here you can see that we're using default member initializers equals 0, but we still have to declare and to default the default constructor, because as soon as you have the other constructor, the default constructor won't be generated anymore for you. Here it's pretty obvious that a score and a name can vary independently. There's probably no constraints between those two. So it looks like a good candidate for using an aggregate instead. So this is what it would look like, a simple struct with the name and the score. And now you don't need the default constructor anymore. So default construction works. It will default construct each data member. And now you have access to aggregate initialization to replace the constructor that you had previously. Also, one bonus that you have, this aggregate initialization is probably better than the constructor you had, because it will pick for each data member individually the best construction method, be it by move, by copy, or in this case, it would choose the constructor from a character pointer, for example, for the string. So if aggregates are so great, we have to know what's allowed in a struct to be an aggregate. So let's start by what is not allowed. You cannot have any private data inside of a struct to be an aggregate. You cannot have any kind of constructors at all. And you cannot have virtual functions. But that's pretty much it. You have a lot of stuff actually that's allowed. You can have default member initializers, so this is the =0 that we've seen previously. You can have more complex data, like a string, for example, which itself is not an aggregate because it has a private data member, but the struct that contains it can still be an aggregate. You can even have member functions, including private member functions. You cannot have private data, but you can have private member functions if you want. You can even have base classes in C++17, and the struct can still be considered an aggregate. You can have destructors, but honestly, if your struct has a destructor, it probably means that it should be a class at this point. And now for a feature that I really like from C++20, it's designated initializers. So this is like the new superpower that's exclusive to aggregates. And it's the closest that we have in C++ to what other languages have to name their arguments in function calls. If we look back at our score entry struct, you can construct it like this now since C++20. So you can use that syntax, .name = neo, .score = 100, to specify each of the data members. And you can skip some if you want. They will be default constructed. But you cannot put them in the wrong order. If you do that, it won't compile. One good use case for designated initializers is default options. So if you've ever written a function that has a lot of parameters with default arguments, you know that it's awkward to use in C++. So let's look at this example here. We have a process function that takes an image and does some image processing on it. Usually, the default values are okay. You don't need to change them. But let's assume that you need a different contrast multiplier in your case. Now, your function call will look like this. You have a process function, and you call it by changing the contrast multiplier to 1.3. But you have to repeat the previous default arguments. And now you can make a mistake by repeating them. What's even worse is maybe somebody later will refactor your function or change the default values. And now, will they update your function call? Maybe not. So this is bad. And actually using a struct or an aggregate in this case for this, it makes it safer and clearer in general. So here we have the struct where we've moved all the default arguments in it. And we have an example, well, we have the declaration of the process function that takes a struct as argument, which is default constructed. And now, if we want to do the same call as before, this is what it looks like. And you just use aggregate initialization with designated initializer to only provide the default argument that you want to override. I find this syntax really neat. Since we're talking about aggregates, another use case in the core guidelines is returning multiple values. So you should generally prefer returning an aggregate to having multiple output pointers to your function. If we take this function as an example, so count non-finite here, counts the number of nans and infinites in a sequence passed as first argument. So to call it, you first declare the two integers and you pass them by pointer. The problem here is the intent is unclear. You don't know whether these parameters are output parameters or in-out parameters. Maybe the function has been meant to be called repeatedly on multiple arrays and accumulate the results. You don't know. And if it's the case, you have to initialize those variables to 0, otherwise you will get garbage. So yeah, the intent is unclear. Also, the variable cannot be declared const in this case. Instead, you can use a struct, an aggregate, to return your values and just return them. It's the mechanism of the language. Now it's unambiguous. It's an output only. Also, if you don't like having the name of the struct, you can use structured bindings in C++17. It works with aggregates too. So you can bind names to each data member. But now it's your responsibility to write them in the right order. So there's a danger there. Also, if you're worried about performance, since C++17, we have mandatory copy and move elision here, in case where the count non-finite function returns a temporary value. So in that case, we're sure that there will be no copy or move. The object is constructed directly in the color space. Also, I would argue that having an aggregate yields way better names than using, for example, pair or tuple. So let's look at those three possible prototypes, one that returns a struct and the other two that returns pair and tuple. Which would you prefer when you read the code? Would you prefer the first one where you access the output using .non-count, the other one using .first, or the third where you say stud : get angle bracket 0? So it seems pretty obvious to me that it's the first one. And even better, the order is not important. I could even change the order here of the element in the structs and it would still work. So safer also. Let me end this section with some general advice. I would say keep things simple when you can. Use well-known idioms by your team. Don't write code just in case you might need it. So don't over-engineer for all possible futures. We've been taught to architect systems that are very flexible. It's a good skill, but plan for the likely. Don't plan for everything. When looking at that online on Wikipedia, I found this quote actually from John Carmack. It is hard for less experienced developers to appreciate how rarely architecting for future requirements or applications turns out net positive. I think it summarized things quite well. I will just change one thing in there if it was me. I would remove the for less experienced developers. Honestly, I think it happens to most of us. It still happens to me anyway. So, as an example of this, it's also in the core guidelines. Don't write trivial get-set functions. So if you're creating a new class that maybe has no invariant, don't jump in and write get-set functions for everything if they're not there to enforce something. So keep your classes simple, and if you can have aggregates, then you have less code. It's easier to understand. But I would put a caveat on that. It's not like a very general rule, in my opinion. It's true as long as you have easy write access, I would say, to your colors code, so that if you need refactoring later, you can still change your colors code. But as soon as it leaves your hand and it's an external API, then now all those techniques like opaque handles, get set functions, and all that becomes really more important, because you need to be able to change your internal representation without affecting your callers, your users. Okay, so now let's zoom in a little and talk about functions and their parameters. It's important that you try and make the intent of your function as clear as you can. And intent can be conveyed in different manners. One way is through naming. So you can select a good name for your functions. But as I was saying earlier, you can also use naming conventions that can help. So for example, maybe in your team, you decide that when you name something get thing, then it's a very fast function. It's not expensive. You can call it whenever you want. But if it's expensive, you call it compute thing, so that you won't call it by mistake in a loop, for example. And if it allocates an object and is a factory function of some kind, then maybe call it create thing instead. Intent can also be conveyed through parameter types. So selecting the right parameters for your functions can help convey whether a parameter is mutable or not, whether there's any kind of ownership transfer involved, and also if the parameter is optional or not. And we'll see more of that later. Also, the intent of your function must be clear at 3 different places in your code base. So the function is visible at the declaration side, so this is in the header, at the definition, so usually in the CPP file, and also at the call site for your users. And it must be clear at those 3 different places. Debug time. So let's look at this function together. We have a small, simple init window function that takes a window and some options. And it takes the size from the user options, resizes the window using that size. It allocates presumably a GPU texture probably with that same size. It binds the texture to the window, clears the window, and displays it on screen. You run it, and it crashes on the clear call. So by experience, you know that at that point, we're probably writing out of bounds somehow. And let's say by experience, you know that this happens when the size of the texture doesn't match the size of the window. But you're looking at the code here, and you're getting the size on the first line, and you're passing the same size on the next 2 lines. So how is it possible? What's going on? So you go and look at the alloc texture function in the header, and this is what you see. Might round the size up to some multiple depending on hardware. Oh no, it's taking the size by mutable reference. And this is bad because it wasn't, in this case, visible at the call site. Mutability was unclear here. And this is why I usually say try to avoid non-const reference parameters when you can, because their mutability is not visible at the call site. C# has solved this, for example, for structs. If you look at the equivalent code here, instead of the ampersand, you would have the ref keyword, but you would also have to write the ref keyword at the call site, and it makes it visible. And for example, Rust has the same with the mute keyword. And now you know that, oh, the function could change that size parameter. So to make mutability visible, again, if it's an output, make it an output. So use return values when you can. In this case, for example, we could change it for a resize function that takes the size as input and returns the new size, even if it's the same as output. And now it's very clear. If you tag it with the no discard attribute also, then you force your caller to assign it. So it's very visible at this point. As another solution, not as good, if you really have to, you can use a pointer. At least it has the advantage of being visible at the call site instead of a reference. But now you have a new problem. That pointer can be null. So it's for you to decide. Be pragmatic in this case, I would say. Decide among your coworkers which cases are acceptable. Another thing that is important to make more visible is the validity of a value. So now let's talk about the pervasive -1 in our code bases. So let's assume we have a get discount price function that does some lookup. Let's say it looks for a customer and it searches for whether that customer has a discount price on a product. If it has, it returns it. Otherwise, it returns -1. So when you use it, you call the function, and you check whether the discount price is valid. If it is, you use it. Otherwise, you use the full price. So the problem here is you could forget to check. Maybe the code will get refactored later, and the person that calls that function doesn't know that it can return an invalid value. Nothing is forcing you to check it before using it. And to handle this, you can use std_optional for that. Since C++17, this type is really either a constructed T or an empty optional. So in this case, you could use it to indicate that there is no discount, so not found, by returning an optional price instead of having an invalid value. And now you don't rely also necessarily on a command that says -1. In this case, the call would look really similar, but the main difference is you have to use the indirection operator here to read, to get the value out. So you cannot forget, it's a different type. But even more than that, in this case, this pattern of using the value inside of the optional if there's one, or using another value instead if it's empty, is so common that there's actually a function for it, and it's called value or. So here it's even more readable. You just call a function. If there's a discount, you use it, or you use the full price. And what's even better, in C++23, we'll get even more helper functions like this one, like value or. Invalid values appear not only for return values, they appear also for parameters. So as an example, let's say you have a getURL function, and that function fetches a web page, but you can provide a timeout if you want. But by default, if you don't want a timeout, you use -1 to indicate no timeout. The call site is very clear, no problem here. Now it's the definition in the CPP file that's unclear. Here, the implementer in the CPP file doesn't know right away that the timeout can be negative. So maybe at some point somebody else will refactor that function and they will forget to check for -1. And now you wait for -1 seconds and you will probably have a bad time. So instead, you can use, again, std optional for that. So in this case, this is what the function would look like. It would take instead std optional milliseconds for the timeout, and by default, an empty optional. And now in this case, it's very clear that, okay, if I don't want a timeout, I just let it to the default value. So the call site remains unchanged. But in the CPP file, again, now you cannot forget to check. That optional has to be dereferenced to get to the value inside. I've modified the same example here, but to use a class, just to show that it also happens inside of classes. So you can have members that are invalid inside of classes. Here, let's say that the timeout can be -1 if you're not using it. And in the fetch function for your URL fetcher, you're using the timeout. But now you have to check it. So it's the same problem. You might forget to check that the timeout is valid or not. So instead, you can use std optional here. This is what it would look like. So now you have a member with optional milliseconds, and you cannot forget to check it. But this has caveats. If you do this inside of classes, keep in mind that optional is often implemented as a T and a Boolean that indicates whether the T is constructed or not. And because of alignment constraints, at least in this case, it means that the timeout takes twice as much space as before. Also, if you're doing this in some kind of loop, let's say you have an update loop and you want to refresh things often and you go from valid to invalid state. Each time you transition from one to the other, you have a constructor-destructor call for your type T. And if it's expensive, then you have to keep that in mind. Maybe a different solution is needed at that point. Here, I've shown an example where the value, we're using -1 to indicate invalid value, but also often Booleans will be used to indicate whether something else is valid or not. And this is, I would say, even worse, because now you don't know what other data members is affected by that Boolean. And maybe there's more than one. Maybe there are multiple data members that are invalid when that Boolean is true or false. So you can replace, again, this by an optional. And if you have multiple data members, you can put all of them in an aggregate and have an optional of that. And you probably have seen a lot of variations on that, like all those Booleans that are called is dirty, is initialized, must update, is cached, all of those kinds of names. Speaking about Booleans, I would say avoid Boolean parameters at all if you can. They're so easy to use. That's the problem with Booleans. So let's look at the display function. You have a display function that displays an image on screen, and at some point your colleague tells you, oh, we have cameras that have an option to mirror the image. So sometimes we have to flip it before displaying it. Oh, I know what I'll do. I'll add a Boolean. I'll add a Boolean to flip the image when I need. And now at the call site, you have that true here. And true doesn't give the reader much meaning. Again, think about the use case, for example, of the GitHub reviewer. They don't have access to the IDE. They don't have any tooltip. What does true mean? It doesn't take a lot of effort to make it really more readable. Just create an enumeration instead. It's not a lot of more code. You just write this enum class here. And now at the call site, it's very clear. You have a name for that true. If you're at the point where you want to add more than one Boolean parameters, then maybe what you really need is the option struct, as we were looking at earlier. And at that point, you can keep it as a Boolean. The problem does not apply anymore, because now you have to name it anyway, so it's OK. Now I want to look at some other guidelines that are related to passing arrays. So since C++20, we have a stud span, which is really an abstraction over a pointer and a size. And it's the main way that is suggested to pass arrays now. So stud span is very flexible because it can point to anything. It could point to stack memory. It could point to a subpart of a vector. But it's also handy because it can be implicitly constructed from stud vector or stud array or C-style array. So if you have a function that takes a span, it can take all of those without any more effort. And without making it a template also. So it's maybe even easier for some people. For this reason, nowadays, you should not use raw pointers anymore to pass arrays. And anyway, if you're doing this, probably you're passing the size next to it. And at that point, you're doing the same thing as passing a span. So just use span. I've summarized here a few usage of span. So the first one is an array. Let's say you want to pass an array, and you want to mutate the elements, but not add element or remove element to that array. Then you would take a span of t by value. This is very cheap to copy. You're just copying the pointer and the size, so you're taking the span by value here. If you want a view of const elements instead, then this might surprise some people. You have to write span of const t and not const span of t. This is not like vector that is deeply const. Span is more like a raw pointer. You have like two consts possible. Is it the pointer that is const or what is pointed to that is const? So here it's the t inside of the span that is const. So this is where you have to put the const. And if you're at the point where you need to add and remove elements to your sequence, that's when span is not good enough anymore. And now you can use something like a reference to a vector or a pointer if you prefer. Also, related to vector, if you have functions, and you probably do, if you have functions that take const vector references, at this point, there is no advantage compared to taking a span of const t. And span will allow more parameter types. So it's a good thing to convert them actually to take span. Because if you're taking a const vector, you're only using it to access the elements. You're not adding elements or removing elements. Let's do the same with smart pointers, so guidelines related to transfer of ownership. You should use smart pointers every time there's a transfer of ownership involved. And if there's not, you should not use smart pointers as parameters. So don't use raw pointers to transfer ownership. because you want to avoid leaks, and this is why smart pointers have been introduced. So again, a small table to summarize the different usage. If you want to transfer ownership to the callee, so you have an object and you want to give the responsibility to your subfunction, you should take the unique pointer by value, again, here, and this is because it's a move-only type. So it's very cheap to move, take it by value to transfer the ownership. If you want to share the ownership, then I would say it's the second choice usually. If you want to share the ownership, then take a shared pointer. And if you want to go the other way around and you want to transfer the ownership to the caller, you have a factory function that allocates something and return it, then you return by value a unique pointer. And I want to point out here that a shared pointer can be constructed from a unique pointer, but not the other way around. So factory functions are more general if they return unique pointers. Also, if there's no change in ownership involved and you have a unique pointer or smart pointer, resist the temptation of passing a const unique pointer reference to your function, because it has confusing semantics at this point. There's no ownership involved. So if you only want to manipulate the object inside, pass the raw pointer. And yeah, I think this concludes the advice I summarized inside of 1 hour. So let us see a little summary and look at all that we've seen. So read the C++ core guidelines. It's the distilled experience of a lot of people in the industry. It will improve the way you code. Promote local reasoning. Keep in mind the GitHub reviewer again. Help them read a small block of code and have enough context in that small block of code. Use simple construct. Don't over-engineer. Keep it simple. If you have any kind of resource management, push it down in your data members and create new abstractions to reuse them elsewhere. And this will let you use the compiler to generate all those special member functions for you. Also, express intent in code instead of comments, for example, by choosing good names and good parameter types. And keep in mind that the function should be clear at the declaration, the definition, and the call site. Finally, if you have any kind of naming conventions or guidelines, you should enshrine them in an onboarding document. This will be really useful for newcomers to your team, and they will boot up faster. Finally, be pragmatic. Build consensus among your coworkers. By following the rules that you set for yourselves, you'll get a consistent code base. And this, I hope, will help you and your teammates write code that is readable and maintainable. Thank you.